Welcome back, learners. In today's lesson, we're going to demystify the core concepts that form the foundation of all machine learning systems. Whether you're a software engineer exploring ML for the first time or a seasoned developer looking to solidify your understanding, this lesson will equip you with an intuitive grasp of the essential building blocks: features, labels, and models. We'll start by clearly defining each concept, then illustrate them with multiple real-world examples. As we go along, I'll share helpful analogies to connect these ideas to concepts you're already familiar with. By the end of this lesson, you'll have a firm understanding of how these components work together to solve complex problems. Let's dive in. 1. Features. The what of machine learning. First, let's talk about features. In machine learning, features are the measurable properties or attributes of the data you're working with. You can think of them as the variables that serve as input to your ML system. Imagine you're building a model to predict house prices. Your features might include quantitative attributes like the total square footage of the house, the number of bedrooms and bathrooms, the lot size of the property, the age of the house in years. You might also have qualitative or categorical features, such as the architectural style of the house, e.g., colonial, ranch, modern. The type of heating system, e.g., forced air, radiant, geothermal. The neighborhood or zip code where the house is located. These features paint a detailed picture of each house, capturing the key characteristics that might influence its price. Let's consider another example. Say you're creating a system to automatically categorize news articles. Here, your features could be the words and phrases contained in the article text, the length of the article in number of words or characters, the publication date and time of the article, the author or source of the article, metadata tags associated with the article. In this case, the features encapsulate various aspects of the article that provide clues about its content and help determine its appropriate category. So, in essence, features are the informative attributes you extract and select from your raw data. They form the basis for the patterns and relationships your machine learning model will learn. Choosing relevant, discriminative features is crucial. Like selecting high-quality ingredients for a recipe, better features lead to better model performance. 2. Labels. The why of machine learning. Next, let's discuss labels. If features are the input to your machine learning system, then labels are the output or the target variable you're trying to predict. In the house price prediction example, the label would be the actual selling price of each house. It's the variable your model is trying to estimate based on the features. For the news article classification system, the labels would be the categories or topics assigned to each article, like world news, sports, technology, or entertainment. Labels can be of two main types. 1. Categorical labels. These are discrete classes or categories, like the news article topics, or binary labels like spam or not spam for an email filtering system. Categorical labels are often represented as integer encodings or one-hot vectors in the actual ML implementation. 2. Numerical labels. These are continuous quantities, like the selling price of a house, the stock price of a company, or the temperature reading from a weather sensor. Numerical labels retain their inherent order and magnitude. In supervised learning, which is the most common type of machine learning, labels play a crucial role in training the model. The model learns to map the input features to the correct output labels by minimizing the difference or error between its predictions and the true labels. It's like a student learning by comparing their answers to a question key. The labels serve as the ground truth or reference for the model to learn from. It's worth noting that labels are not always readily available. In some cases, like fraud detection or medical diagnosis, assigning accurate labels may require significant human expertise and effort. Techniques like active learning and weak supervision can help address this challenge by strategically involving human input in the labeling process. So, to recap, labels are the target outputs or ground truth values that guide your machine learning model's learning process. They provide the supervisory signal for the model to adjust its parameters and improve its predictions. 3. Models, the how of machine learning. Now that we understand features and labels, let's put them together with the central component of machine learning, the model. In traditional software development, you explicitly define the rules and logic for transforming inputs into outputs. You write conditional statements, loops, and functions to precisely specify how the program should behave. In contrast, machine learning takes a different approach. Instead of hard-coding rules, you provide the model with examples of inputs, features, and their corresponding outputs, labels, and let the model learn the underlying patterns and relationships on its own. You can think of a machine learning model as a mathematical function that maps features to labels. During training, the model adjusts its internal parameters to minimize the difference between its predicted outputs and the true labels. This process is called optimization, and it typically involves techniques like gradient descent to iteratively update the model's parameters in the direction that reduces the prediction error. There are many different types of models, each with its own architecture and learning algorithm. Some common examples include linear regression, a simple model that learns a linear relationship between input features and a numeric output label. It's often used for tasks like predicting housing prices or sales forecasts. Logistic regression, similar to linear regression, but used for binary classification problems where the output label is a categorical variable with two classes, like spam or not spam. Decision trees, a model that learns hierarchical decision rules based on input features to predict categorical or numeric labels. Decision trees are often used for tasks like medical diagnosis or credit risk assessment. Neural networks, a powerful and flexible class of models inspired by the structure of the human brain. Neural networks can learn complex nonlinear relationships between features and labels, making them well-suited for tasks like image recognition, natural language processing, and recommendation systems. The choice of model depends on various factors, including the type and complexity of the problem, the size and quality of the training data, and the computational resources available. As an example, let's consider a model for predicting customer churn at a telecommunications company. The features might include the customer's demographic information, age, gender, location, their usage patterns, minutes used, data consumed, international calls, their account information, contract type, billing amount, tenure, their interaction history, customer service calls, complaints, promotions. The label would be a binary variable indicating whether the customer churned, i.e., canceled their service, or not within a given time frame. The model, which could be a logistic regression or a decision tree, would learn the patterns and factors that contribute to customer churn based on historical data. Once trained, the model can be used to predict the likelihood of churn for new customers, allowing the company to proactively intervene and retain at-risk customers. So, in summary, the model is the heart of a machine learning system. It's the component that learns the mapping from input features to output labels by example, automatically discovering patterns and relationships in the data. 4. Training data versus new data. Now that we've covered features, labels, and models, let's discuss a critical distinction in machine learning: training data versus new data. Training data is the dataset used to teach the model. It consists of examples where both the features and the corresponding labels are known. For instance, in the house price prediction example, the training data would include historical records of houses with their features, square footage, number of bedrooms, etc., and their actual selling prices, labels. The model learns from this data by identifying patterns and relationships between the features and labels. For example, it might learn that larger houses tend to sell for higher prices, or that houses in certain neighborhoods have a premium. Once the model is trained, it's ready to make predictions on new data. New data refers to unseen examples where the features are known, but the labels are not. For instance, when a new house comes on the market, the model can use its features, square footage, location, etc., to predict its selling price. The key difference between training data and new data is that training data is used to teach the model. New data is used to test the model's ability to generalize and make accurate predictions on unseen examples. This distinction is crucial because a model's performance on training data doesn't always reflect how well it will perform on new data. A model that performs perfectly on training data but poorly on new data is said to overfit. It has memorized the training examples rather than learning generalizable patterns. To avoid this, we use techniques like cross-validation and regularization to ensure the model performs well on both training and new data. 5. Framing problems in ML terminology. Before we wrap up, let's talk about framing problems in ML terminology. This is the process of translating a real-world problem into a format that a machine learning model can solve. For example, let's say you work for an e-commerce company and want to improve customer satisfaction. One way to frame this problem in ML terms is to predict whether a customer will leave a positive or negative review based on their purchase history and interaction with the website. Here's how you'd break it down. Features: customer demographics, purchase history, time spent on the website, number of support tickets, etc. A label: the sentiment of the review, positive or negative. Model: a classification model like logistic regression or a neural network. Another example: suppose you're building a system to detect fraudulent transactions. You frame the problem as follows. Features: transaction amount, location, time of day, user behavior patterns, etc. Label: whether the transaction is fraudulent or legitimate. Model: a binary classification model like a decision tree or support vector machine. Framing problems in ML terminology involves 1. Identifying the goal of the system, e.g., predict house prices, classify emails. 2. Defining the features that influence the outcome. 3. Determining the labels that represent the target output. 4. Selecting an appropriate model to learn the relationship between features and labels. This process ensures that the problem is well-defined and that the machine learning system is aligned with the real-world task it's meant to solve. Putting it all together. Now that we've covered the key building blocks, let's see how they fit together in a typical machine learning workflow. 1. Data collection and preparation. Gather raw data from relevant sources, databases, APIs, sensors, etc. Pre-process the data by cleaning, normalizing, and transforming it into a suitable format. Extract and select informative features from the pre-processed data. Split the data into training, validation, and test sets. 2. Model training. Choose an appropriate model architecture based on the problem and data characteristics. Feed the training data, features, and labels into the model. Use an optimization algorithm to adjust the model's parameters to minimize the prediction error. Evaluate the model's performance on the validation set and tune hyperparameters if necessary. 3. Model evaluation. Assess the trained model's performance on the held-out test, set to estimate its generalization ability. Use appropriate evaluation metrics, e.g., accuracy, precision, recall, based on the problem type. Analyze the model's strengths, weaknesses, and potential biases. 4. Model deployment and monitoring. Integrate the trained model into a production system or application. Apply the model to make predictions on new, unseen data. Monitor the model's performance over time and collect feedback from users. Periodically retrain and update the model as new data becomes available. Throughout this process, it's crucial to maintain a close connection between the machine learning system and the real-world problem it's intended to solve. This involves collaborating with domain experts, interpreting the model's predictions in the context of the application, and ensuring that the system aligns with ethical and legal requirements. As you can see, the interplay between features, labels, and models forms the core of the machine learning paradigm. By providing a model with relevant features and accurate labels, you enable it to learn patterns and make predictions that can drive intelligent decision-making and automation. In the next lesson, we'll dive deeper into different types of machine learning, including supervised, unsupervised, and reinforcement learning, and explore how these building blocks adapt to each paradigm. Until then, keep practicing your newfound knowledge by identifying features, labels, and potential models in the real-world applications around you. Happy learning. And there you have it,